Hello, good evening, good day, everybody, and welcome back to the Ask Abhijit show. Today, we are going to discuss science. We're going to discuss space and everything related to all of these matters. So, I have chosen a number of questions that you have asked in the comments, and I'm going to take those. But before we do that, let us see who all is there on the live chat. I can see Sheikh Rayan, Lage Raho online, Ashutosh Pandey, Rahul Kumar, Mac4J1U, Ayush Singh, Krishna of the Surinamese Netherlands, Udbhav Sharma, Ayush Yadav once again, Geopolitical Dubey, Samrat Shukla, Advait Ashwini, Priyanshi Sood, Conservative 168, Navanita Das 3746. Who else do we have? We have Hensi Penguin, uh, Abhishek Sonavane, Advait once again, Navanita Das, Mayank Antil, Surya Pratap, Samrat Shukla, Abhyuday Singh, Shri Vatsa, Rahul Kumar, Ultimate Power A1, Hensi Penguin once again, Kishore 619, Mayank, Rahul Kumar, Real Vladimir Putin is here, Aryan Rocking Gaming is also here, Real Painter says glory to Indra. Good to see that. And everyone else. Ivan Roy is also here. Konichiwa Nirvana Shanks. God was alive. Aryan Rocking Gaming, Nirvana Shanks, Conservative, Advait Ashwini, Balki today, Samrat Shukla, Nirvana once again. Ankita Kachap is here. 7i Atlas is here. SHSJ09. Anand Sutram is here. VSVS 2400. Namaste. And thank you so much. Namaste ji. Advait Ashwini and everyone else. So let's get going with the questions. What questions do we have? I'll take as many questions as possible today. Manisha Cardozo, namaste. Everybody else, namaste. So let's take some questions. Let's get going. I've chosen questions that will hopefully appeal to and hopefully give value to as many people as possible. So what are the questions? Let us begin. Critical thinker says, is the universe infinite? Universe, is it infinite? And what is its overall shape or topology? That's a great question to start with. Is the universe infinite? What's the shape of the universe? What's the topology of the universe? So let's say you go out of wherever you are and it's nighttime and you look up at the night sky and you see all the stars and whatever else you see out there in the night sky. So you could ask yourself, is this all there is? Everything I see in this specific direction, how far does it go? Does it go all the way to infinity? Or does it stop at a certain distance from where I am? And is there something beyond it? That's a great question. It's a fascinating question. It's something that humans, our ancestors, most likely have been asking since the beginning of time, possibly, right? So what's the deal? So here's what we know. Look, the universe, as far as we know, the best understanding that we have is that the universe began about 13.8 billion years ago. And it expanded very rapidly in a phase called inflation, which was superluminal, which was space-time expanding faster than the speed of light. And then it slowed down, but it's still expanding right now. And the expansion of the universe is accelerating. And all the light that reaches us has had 13.8 billion years to reach us. So whatever we see, whatever stars, galaxies, etc. we see, their light has only had a certain amount of time to reach us. But it's possible there may be other stars, galaxies, and whatnot that may be further away, so far away that their light hasn't had time to reach us yet. So the universe has been expanding for 13.8 billion years, and the amount of light that's able to reach us as of today, that has a radius, let's say from us, a distance of about 40, what is it, 46, 47 or so billion light years. So it's like we are in a bubble. We are in a bubble with us at the center, a spherical bubble, and the diameter is about 93 or 94 billion light years, and the radius is half of that. So that is the amount of universe we can actually observe. Okay, that's how much we can see. But that doesn't mean that that's all that exists in the universe. Most likely there's way more universe beyond what we can observe, but it's so far away that its light hasn't had time to reach us yet, and maybe not maybe most likely it will definitely never reach us, because now the universe is expanding, its expansion is accelerating, and at the edge of the observable universe, the expansion of the universe is so fast that it exceeds light speed. And it's not breaking the laws of physics, because it is space-time that's expanding. It's not light traveling faster than the speed of light. That's not like that. It's not matter traveling faster than the speed of light. It's space-time itself, the fabric of the universe itself expanding faster than the speed of light. Okay, so the universe that we can observe has a diameter of about 94 billion light years. But there is a universe beyond that, that is for sure. So the question is, how large is the actual universe beyond what we can observe? And what's its shape? What's its topology like? So let's talk about shape. We know that we are immersed in something called space-time, the fabric of space-time, 4 dimensions. It's got 3 dimensions of space, length, breadth, height, and the 4th dimension is the dimension of time, right? But let's talk about the spatial dimensions, the 3 dimensions of space, length, breadth, time. So if we take, remember school level geometry. If you have a flat sheet of paper and you draw a triangle on this flat sheet of paper, then the sum of the angles adds up to 180 degrees. But that only works for a flat sheet of paper. If you have, let's say, a sphere, you draw a triangle on a sphere, you will find that the sum of the angles adds up to more than 180 degrees. Sorry, 360 degrees, right? So the sum of the angles of a triangle on a curved surface, such as this one, a spherical surface, adds up to more than 360 degrees. And this is what we call positive curvature. So on a flat sheet of paper, you have neutral curvature. You have no curvature. On a surface like this, you have positive curvature, in which the sum of the angles adds up to more than 360 degrees. But there is a third kind of curvature, which is called negative curvature, which is a saddle-like shape. In that, you will find that the sum of the 3 angles adds up to less than 360 degrees. So 3 kinds of curvature: neutral or zero curvature, positive curvature, which is this, and negative curvature, which is a saddle shape. Now the question is, what is the curvature of the universe? What's the curvature of space, of the space that we inhabit? And if you're a cosmologist, you can measure that by looking at various spots in the afterglow of the Big Bang, which is the cosmic microwave background radiation. So you can look at various spots in the CMBR, and you can, based on that, calculate what is the curvature of space. Now, what we find is that the curvature of space of our universe seems to be very close to zero. It's very close to zero, which means that the universe is most likely flat. Now, if the universe is flat, it means there is no curvature like this, which means there's a high possibility that the universe could be infinitely large. Okay, so that's one possibility. The other possibility is that, to the best of our calculations, the curvature is almost zero, but maybe it's not quite zero. So it could be that the universe is just gigantic beyond our wildest imagination. So if we are standing on the surface of our planet Earth, do we see any curvature? We don't, right? It seems flat. We see the curvature only when we zoom out and go at a very high altitude. That's when we start seeing the curvature of the surface of our planet. So maybe it's like that. Maybe the universe is gigantic, unimaginably large, and the curvature is negligible the way we see it. That's another possibility. So that is the answer to the shape of the universe. Maybe the shape is just flat, which means the universe is infinitely large, or maybe it's just very slightly curved, which means it is gigantic beyond anything we can even possibly conceive or imagine, right? And then when it comes to topology, topology. So topology is like, see, the universe could be flat, space-time could be flat, but it could be looped. So if you play computer games, okay, and you have let's say a square screen, let's say the game called Pac-Man. Let's Google what is Pac-Man so that you get an idea of what I'm talking about. Okay, Pac-Man. That's like a primitive game, 1980s kind of game. Okay, and you have this screen over here, and the Pac-Man creature, if it goes all the way to the right and goes beyond the edge of the screen, it reappears from the left. So it's gone beyond the edge of the screen from the way we see it, and it reappears on the left. But if you are Pac-Man, then you might feel that the universe you inhabit is infinite, but it's actually a looped universe. So that is another possibility, that maybe the universe is looped. It appears it is flat, but it is still looped. So that could be its topology. But all of this, what I'm saying right now, it's all speculation. We don't have the data. We don't have the actual data to back up any of these speculations. But from a mathematical perspective, it kind of makes sense that either the universe is flat and infinite, or it is just very slightly curved, which means it is gigantic beyond belief, or it is flat but looped, which is why it is not infinite, but the curvature is still zero or flat. And there are ways of trying to prove or disprove whether it is flat but looped. So what you do is you look for repeated pixels in space. So you see a cluster of, let's say, stars and galaxies or whatever in one patch of space. You try and look for the exact same cluster or the same other exact same pattern somewhere else. But thus far, we haven't discovered that. So at the end of the day, the most accurate physics answer is that we don't know. The observable universe is finite. It's got a diameter of about 93 or so billion light years. The actual universe is larger than that. It appears to be flat or very close to flat, which could indicate that it's either infinitely large, or maybe it is flat but it is looped. But we don't have a way of telling which way it is right now, because our instruments, our methods of detection, etc., are still very primitive. Maybe in the future we'll have a better understanding of what the real situation is like. So the observable universe is finite. The real actual universe may or may not be infinite. We can't say for sure right now, based on our 21st century understanding, the best 21st century understanding of physics. Next question. Advait says, time is not absolute, but it's relative according to general relativity. Then when we say that the universe is 13.8 billion years old, what are we talking about? Because time is not constant throughout the universe. What are we talking about? That's a great question, isn't it? That's a brilliant question. So what do we mean when we say that time is not absolute? Time is relative according to general relativity. So here's the deal. Time flows, let's say it flows at different speeds in the universe. Okay? If you are free floating in empty space with no large gravitating body near you, then time will flow at a certain speed, at a certain rate. But if you are near, let's say, a black hole, let's say you are near a black hole, it may not look bumpy like this, but it's the best I could find to a black hole. So if you are near a black hole, the closer you are to it, the slower time flows for you, right? Now, let's say you are sitting on a rocket on the ground. Then your time, the rate at which time flows for you is the same, essentially, almost the same as the time outside the rocket. But let's say your rocket lifts off and goes off into space at a very high velocity. Let's say half of light speed. Okay, as an example. Then if you are sitting inside, for you, time is the same as it was before you left. But if you have a twin brother or sister on Earth that you left behind, and let's say you go on the journey, it takes you 1 year, you return, you may find that time has gone forward by several decades on Earth, and your twin is like 70 years older than you are, because time flowed at different rates. For you, it slowed down. For your twin, it proceeded as usual. So the rate at which your clock ticks depends on whether you are going fast or slow, and whether you are close to a gravitating mass or not. So if you are, let's say, living on a planet that's orbiting a black hole since the time the universe began, then by now, maybe for you, only 5 billion years have passed, perhaps. as an example. But for us on Earth, 13.8 billion years have passed. So you see, for them, for that alien species, only 5 billion years have passed since the beginning of the universe. But for us, it's been 13.8 billion years. So time has flown at different speeds. And similarly, if you're on a rocket as opposed to not being on a rocket, it once again makes a difference as to how time flows. So then, when time itself is not absolute, when it is relative, how have we decided or deduced that the universe is 13.8 billion years old? That's a great question. Now you understand, hopefully, the context in which we are operating here. So, see, the universe has two interesting properties. It is homogeneous and it is isotropic. What does that mean? It means that when you zoom out and look at the universe, not at the scale of centimeters or meters or kilometers or even light years, when you look at the universe at the largest scales, where galaxies come together in superclusters and superclusters come together in filaments, scaffold with the scaffolding of dark matter, when you look out at that incredibly large scale, then the universe seems to have the exact same composition in all directions. It's homogeneous at the largest scales. At the micro scales, it may be granular, it may not be homogeneous, but at the largest zoomed out scales, the universe is homogeneous. It's also isotropic, which means that no matter which direction we look at in the universe, it seems the same. So it's homogeneous and isotropic. And the universe is mostly empty space. So let's say that we we know that the universe has been expanding. It's been expanding ever since it formed. That's the entire thing about the Big Bang. It was not an explosion, it was an expansion of space-time. Right? So the expansion of the universe, the expansion of space-time is like, imagine you are blowing a balloon that way. The balloon is this small, and you blow air into it, and it becomes larger and larger. And let's say you've got a bunch of ants on the balloon. In the beginning, they're all together. But as you expand the balloon, any two ants, if you look at them, the distance between them increases, even though they are not walking around. They're just sitting there. But the distance between them increases. And the larger the universe gets, the more and more they get apart, any two ants. Right? So that's the way the universe has expanded. Now, let's say that the moment the universe began expanding, let's say we put a whole bunch of clocks in various parts of the universe, a very large number of clocks. You see, clocks. You see, clocks like these, we sprinkle them all across the universe in regions of the universe where there is no major gravitational field. So far away from big masses, so that the clocks are not influenced or slowed down by the presence of a nearby gravitating mass. So let's say we sprinkle a very large number of such clocks all across space in the universe, and let the universe expand, and let the clocks, like those ants on the balloon, drift apart from each other with the expansion of space-time. So the clocks are stationary in space, but space-time itself is expanding, so the clocks go further and further away. And they are not influenced by motion within space-time, which can influence the rate at which the clock ticks, and they are not influenced by the presence of any nearby major massive gravitating object. So the clocks, they run at a speed that is not influenced by any relativistic effects. And then see how much time they measure, right? And then and if you measure the amount of time that's elapsed since the beginning of the universe until the present day, you will find it's about 13.8 billion years. And obviously we did not go back to the beginning of the year of the universe, to the Big Bang, and sprinkle a gazillion clocks across space-time. We did not do that, but that's the theory. Now, how do we deduce the way it's actually happened? Well, we look at various effects and we add all of them up, and we do it in a multiplicity of ways. We factor in the amount of mass in the universe, the amount of redshift, and so much whatever else, and we add that up, and to the best of our understanding, the universe, as far as we know, is about 13.8 billion years old based on all those calculations. But this is the basic theory behind it. We sprinkle clocks all across the universe and measure their proper time, and that gives us the actual age of the universe. So that's how we know despite time not being absolute, despite time being relative according to GR. That's why, despite that, we know that the universe is 13.8 billion years old based on this theoretical framework. Okay, Surya Pratap says, what is entropy in simple terms? Entropy is an old friend of mine. I've had lots of very, very, very interesting arguments, let's say, about entropy. Okay, about what is entropy. What is it? So, what is entropy? If you read a textbook, okay, a basic physics textbook, it will say entropy is the measure of disorder of a system. Okay, what on earth does it mean? Do you understand what it's trying to tell you? Entropy is the measure of disorder of a system. If you are a beginner with no background in theoretical physics, it will make no sense to you. Entropy is the measure of disorder of the system, of a system. So let me try and make it more intuitive. Let me try. Let's say you have a room. I have a room, right? I'm in a room here. You can see all the books behind me are nicely arranged. There's a nice little rhinoceros over here. Yeah. Go back, bro. So we have this nicely arranged room that I am in. Okay. Now let's say we have another room. Before we go to the other room, this is a nicely arranged room, right? Now let's say I take this rhinoceros and put him upside down. Will you notice? I think you will notice very quickly. Let's say I take these books and disorder them, pull some of them. Well, that's disorder. So let's say I do that sort of thing. You will notice the rhino fell down. The books are, placed haphazardly. Some books have been pulled down and so on. So in a very orderly room, a little bit of disorder, you will notice immediately. Now, let's say I have a different room, which is an absolute mess. Let's say it's a room with bookshelves, there's a bed, there's sofa, the furniture, and I have thrown books on the floor, I've thrown books on the bed, I've thrown books on the sofa, I've thrown clothes on the bookshelf, I've got cables all over the floor, I've got dust or cobwebs all over the walls, pens and stationery strewn everywhere. And let's say you enter that room and you will see chaos, you'll see an absolute mess. Now you go out of the room for 2 minutes. In those 2 minutes, I will rearrange the mess, make it not less messy, but different kind of mess. Then you come back after 2 minutes. Will you notice any change? You will just notice a mess, right? It's just a mess. There's no pattern to it. So even if I have rearranged the mess and thrown some books there and some clothes here and rearranged the cables in a different messy way, you won't really notice it. That room with a mess is high entropy. This room with less mess is low entropy. So then, now that I've explained these two rooms to you, let me try and explain what entropy is. Why is one room high entropy? Why is the other room low entropy? A low entropy system like this room is such that even if you make a small change in it, you will notice it. You'll notice something has changed. A high entropy system is like that horribly messy room where even if you mess things around more, you will not be able to notice that there's been a change in the mess. So a system in which you can make major changes without anyone noticing at a large scale what's happened is a high entropy system. The more change you can make without anyone noticing, the higher the entropy it is. And in a low entropy system, you will be able to notice a change even with a small change, right? So that's kind of an intuitive explanation of what entropy is. So now let's talk about actual physics. Let's say you have an ice crystal. Okay, an ice crystal. It's a very orderly arrangement of molecules. A block of ice, or an ice cube. It's a very orderly arrangement of molecules. It's a crystalline structure, ice crystals, right? So that's a low entropy system. A small change will be noticeable because the structural integrity of the of the block will degrade. So if you have an ice crystal, okay, a block of ice, and you put it in a warm room for even a minute, you'll start noticing that the outer surface becomes liquid, it starts melting. You'll immediately notice. So that's a high entropy system in which a small change is immediately noticeable or very easily noticeable. Similarly, if you take that ice crystal and you put it inside a glass of water, it will immediately start dissolving and you'll be able to see it. So that's a low entropy system, that ice crystal. Another example of low entropy is, let's say you have a box in which there is a gas. And let's say for some reason, all of the gas molecules, they go and stick to the right end of the box, right side of the box, and everything else is vacuum in the box. Then those gas molecules, they'll obviously turn liquid and you will see it, right? It's certainly visible. But that is not sustainable. So it will immediately go back to gas and you will immediately notice the change. So there, a low entropy system became transformed into a high entropy system. Now, let's say you have a box in which contains a gas. And let's say there are 1 trillion gas molecules in there. And let's say you shake the box and rearrange the gas molecules in a totally different configuration. Will you notice anything? You will notice nothing because it's a high entropy system. Okay, so that's what we mean by entropy being the measure of disorder. So when something changes in a system and you can't notice a thing, that's a high entropy system. And when even a small thing changes in a system, but you notice it immediately, that's a low entropy system. And nature always prefers high entropy. So any natural system typically goes from low entropy to high entropy, from less disorder to more disorder. That's how it typically goes. Another way of thinking about it is that entropy is tied to energy, right? So things go from from a certain configuration of energy to a different configuration of energy. For example, once again, that block of ice, okay, it's a pretty low energy system compared to a glass of warm water. When you have ice at -3 degrees centigrade and you have a glass of warm water at, let's say, 25 degrees centigrade, that's the glass of water at 25 degrees is a higher energy system compared to the block of ice, which is at a much lower temperature. Now, if you put the block of ice in that glass of water, the temperature very rapidly starts to equalize, right? And that's how you see that the energy is distributed in a certain way and the entropy rises. So that's entropy. And so, like I said, the second law of thermodynamics says that nature always prefers higher entropy systems. The total entropy of a system will either stay the same or it will increase, it will never decrease. That's the second law of thermodynamics. Now you will say, how is it that possible? I take water, I put it inside a freezer. After 30 minutes, I've got ice. So hasn't the entropy decreased? Yeah, the entropy has decreased locally. But your refrigerator, in which you have a freezer, how does it create the ice? By sucking out, let's say, the heat from that enclosed space, but it spews out that heat by increasing the temperature of the surrounding air. And if you look at the total change that's happened, thermodynamic change, then there's been more disorder to create a certain amount of order. So in the freezer, the entropy has decreased, but overall, the entropy has increased slightly. That's how it goes. So that is entropy in simple terms. It's a statistical measure of things. A single particle, a fundamental particle, cannot have entropy. It's only a collection of particles or objects that can have entropy. That is entropy in simple terms. Hopefully now this explains what we mean by it's a measure of disorder. It's the amount of different ways in which you can reconfigure a system without anyone noticing or anyone caring. So let's say I have a box of gas molecules and I shake it around and it's now a different configuration. But do you care if the configuration has changed? For you, it's just a gas, right? It has no noticeable effect that matters on the world. So that's a high entropy system. But in case of a block of ice, it's very easily noticeable and it changes, things change. So that, in short, is what entropy is. Next, critical thinker says, how does gravity affect aging or time itself? Do a person's feet age a little bit faster than the person's face or the person's head? Yes, gravity and aging and gravity and time. So we are talking about general relativity over here. General relativity is the theory that Einstein came up with, and it's our best theory of gravity to date. Uh, Physicists have been trying for close to a century to find a way to break this theory, to prove it wrong through experimental means. They've been testing it to its limits, and it's never broken. It's the best theory that we have, experimentally tested theory. So, how does general relativity work? What's the basis? What's the basic premise of general relativity? The basic premise of general relativity is that the world we live in is made up of a four. We inhabit a four-dimensional stage. The four dimensionals are length, breadth, height, the three dimensions we are familiar with, and a fourth dimension, which is time. So time itself is treated as a dimension in general relativity. And taken together, these four dimensions, they form the four-dimensional fabric of space-time. Now, according to general relativity, the presence of mass warps or curves the fabric of space-time. And the curvature of the fabric of space-time tells mass how to move. So if you have space-time with no mass in it, it's just, you could say, non-curved, you could say flat. And all lines are straight in that case. But the moment you place a mass in space-time in that four-dimensional fabric, it all curves up, it warps, and the lines are no longer straight. So the mass, the massive object, has to travel across curved lines, and that's why that causes the effects that we consider to be, gravitational effects, like the orbits of planets around stars, the orbits of stars around galaxies, and so on. Now, so far we're talking about spatial curvature, and curved orbits and curved paths that massive objects take because of the presence of mass. But this curvature of space-time is not just the curvature of space, it's also the curvature of time. So time itself is curved. Okay? Time itself is curved. So the closer you are to a massive object, the more you will find time being curved. Curvature of time. And the further you are from a massive object, the less you will find time being curved along with space. And it is, if you do the calculations, you will find that it is the curvature of time more than the curvature of space that creates the effect that we consider to be the force of gravity. Why do we have weight? This effect called weight is because of the curvature of time more than space. Okay. Now, I'll not go into the equations to explain and prove that, but it is the curvature of time more than space that causes the effect that we call gravity. Now, the closer, like I said, the closer you are to a mass, the slower time flows and the more time is curved. So if you are standing, if you spend the majority of your life standing, then your feet are closer to the center of our planet than your head. Let's say you are an average person 1.7 meters tall, and let's say you live let's say you live 80 years. Let's say you're 80 years old today. Okay. So if you measure the time difference, see, like I said, clocks. If I take this clock and I put it on the surface of the planet, it will tick at a certain rate, and it's closer to the center of the planet. If I take this clock and I put it 1.7 meters above the surface of the planet, it will tick slightly faster, very, very slightly faster. And if you measure the difference over 80 years, you will find that it will be of the order of 1 microsecond. That is almost nothing, but it is definitely measurable. So at the age of 80, if you've spent most of your time on your feet, okay, 2/3 of the day on the feet, your head is about a microsecond older than the feet. Not younger, older. The feet are closer to the mass, so they age slower. The head is further from the mass, so it's going to age faster. If you live most of your life at a altitude of let's say 3 kilometers above sea level, then you will age slightly slower than a person who lives at sea level. If you are in a spacecraft orbiting the Earth at let's say 200 kilometers above the surface, you're gonna age faster than a person who is at sea level. So the higher you go above the planet, the faster you age. And the closer you are to sea level, the slower you age. And this is something that we see that we have to incorporate in GPS satellites. So GPS satellites, they travel at a certain speed around the planet, and they're at a certain height above the planet. They are typically geostationary, right? That's about 36,000 kilometers above sea level. So because they are so much faster, so much higher, they will tick faster than somebody who's at sea level. And the speed at which they're traveling also makes a difference, right? So because it's higher, it's ticking faster, but because it's going faster on the planet, it ticks slower. So you have to subtract the two effects from each other to come up with the exact speed at which the clocks will tick on a GPS satellite. And if you don't incorporate that time difference, your GPS readings will be off by kilometers in just a few days. So that's another proof of the validity of Einstein's theory of general relativity. So basically, that's how gravity affects aging and the passage of time. The closer you are to the planet, or to the center of the planet, the slower your clock will tick by a very small amount. And the higher you are, the faster your clock will tick. And that's why your head is older than your feet. Himanshu Sharma says, is time a fundamental property of the universe, or is it an emergent property that emerges from something? Do you think that time is a basic property of the universe or something that arises from deeper physics? Interesting question. So what is a fundamental property? What is an emergent property? Think about the game of chess. You play the game of chess. I'm sure everyone's tried at least at some point in their life. In the game of chess, you have all these chess pieces, and each piece moves in specific ways, right? The knight will move in a certain way, 2.5 steps. The bishop will move diagonally. Pawns can first take 2 steps or 1 step, but then only 1 step onwards, and they can annihilate each other only diagonally, and so on. Rooks can move in a certain way, etc. So these rules that are part of chess, can you derive them from first principles? You can't. The rules are the game of chess, right? So the rules are a fundamental property of the game of chess. They don't emerge from other principles, from the chessboard or whatever. The rules are the game of chess. So the rules are a fundamental property. An emergent property could be something else, something that can be calculated, or something that can be derived from something more fundamental. So now when it comes to time, right, we are told that the universe, we are not told, we have calculated that the universe is 13.8 billion years old. That's the best calculation, that's the best understanding that we have as of today. So the question is, we talk about time. Did time begin at the moment of the Big Bang? Was the moment of the Big Bang time t equal to 0 seconds? And then time started ticking, let's say, forward. Time t equal to 1, t equal to 2 seconds, and so on until where we are today. So did time begin with the Big Bang itself, or is time something that is a consequence of something else that is inherent or fundamental to the properties of the universe? That's the big question you're asking, which means that is time emergent? Could you have perhaps atoms or molecules of time? Could time be quantum mechanical in nature? Could there be quanta of time, etc.? Right? And was there a time when there was no time itself? Right? That's the kind of deep questions we are asking over here. Now, there are certain theories that approach time differently, which could perhaps give us an answer. So the two best theories that we have of physics today are, one, general relativity, and second, quantum mechanics, quantum field theory. General relativity is the theory of the universe at its large scales, and quantum mechanics and quantum field theory is the theory of the universe at the smallest scales, the quantum scales. And these two theories, they treat time very differently. In general relativity, time is part of the fabric of the universe itself. It's one of the four fundamental dimensions of the universe. Yeah, the presence of mass messes around with time. It curves and warps time, makes it move faster or slower, etc. But time is still a fundamental dimension of the universe, which means that time was there when the Big Bang happened, because you have four dimensions of the universe, and time is one of those four dimensions. So according to general relativity, which is the most rigorously tested theory that we have, time is fundamental according to general relativity. When it comes to quantum mechanics, quantum field theory, time is very different. Okay? If you study basic quantum mechanics, starting from the beginner level, let's say you read Griffiths, you study Griffiths, what you'll find is that the Schrodinger equation has time. It's got a time parameter, t. And various other equations, etc., various other treatments in quantum mechanics have the time parameter, but this time parameter is an external classical parameter. It's not something that's inherent to quantum mechanics. It's an external parameter that we use in quantum mechanics. And to say, yeah, so according to quantum mechanics, time is non-quantum, and it is an external classical parameter. So that once again tells you that quantum mechanics isn't able to explain what time is. It treats time as a fundamental external parameter. So once again, just like general relativity, quantum mechanics treats time as kind of a fundamental parameter. So these two theories, the best two theories that we have, they seem to be telling us that time is fundamental, at least to the best understanding that we have. Now there is a theory which is not proven, but it's this theory which says that time could be an emergent property that emerges from quantum entanglement. So quantum entanglement is this one of the weirdness, one of the weird things that comes out of quantum mechanics, which says that in quantum entanglement, let's say you have two entangled particles. It means that these two particles have properties that are inherently correlated in a way that is non-classical. It's only purely quantum mechanical, which means that they don't have separate wave functions. In more technical language, they have a single wave function that describes both the particles. And no matter where you are, let's say I have one particle here on Earth, and I have another particle on Mars. If I measure a specific property of this particle here on Earth, I will immediately, instantaneously know the corresponding property of the other corresponding particle on Mars. So there seems to be something very strange happening, but we're not quite 100% sure what that is. But so according to this theory, time could be a consequence of quantum entanglement. But that's just a theory. We haven't proven or disproven that thus far. And then when it comes to the arrow of time, see, if you take the equations of classical physics, Newtonian physics, for example, equations of motion, etc., you will see that they contain the time parameter t, and they work backwards as well as forwards. So you can take t in the past, you can take t in the future, and the equations work just fine, right? So according to, it looks like time has no direction in Newton in physics, right? Because you can the equations work both ways. But from our experience, time has a direction. The past is in the past, the future isn't known yet. So even though the equations can tell you about the past and the future equally well, we can only remember the past. We can't remember the future, can we? There is this block universe concept in general relativity, in which the universe is this four-dimensional block in which the past, present, future are all have happened at the same time, but we can't access the future for whatever reason. So what could be the reason why we can't access the future? We can only stumble upon it one second or whatever at a time. Why is that so? That could perhaps be because of entropy. Yeah, that could be because of entropy, because like we discussed when we discussed entropy, the universe always moves towards a state of higher entropy from a state of lower entropy. So you can break eggs, but you can't spontaneously recombine them. You can melt a piece of ice in a glass of water, but you can't spontaneously bring the piece of ice back, the ice cube back. You can't, right? So because of any system inexorably over time moving towards a higher entropy state, that could be the reason why we have an arrow of time that only goes in one direction. It doesn't go backwards. Otherwise, we would remember both past and future at the same time, but we don't. That is most likely because of entropy. So coming back to the question, is time fundamental or emergent? Well, general relativity seems to be saying that time is fundamental. Quantum mechanics seems to be saying that time is fundamental. And that's the best understanding that we have right now. Beyond that, time is a mystery. Time is something we only vaguely sense. I'm not even sure if other animals sense time. Do animals sense time? I mean, we have experience of animals, dogs, cats. These are our, animals we are closely associated with: dogs, cats, cows, elephants. These animals do have memories. They do recognize people that they've seen in the past. But do they understand that there is something called time that is passing and people age? And etc. We're not quite sure if animals have that sense that time is passing. They have memories, but we're not quite sure if they grasp that there is something called time. It seems that we are most likely the only species that grasps the concept of time, that there is something called time and it's passing, but we ourselves have a very vague sense of what time is. So time is probably one of the biggest mysteries in physics, and that's what I can say as of now. Rahul Dunake says, what are the virtual particles that come into existence in a vacuum, making absolute emptiness of space a pipe dream? Are those virtual particles superluminous? Why is this name virtual particles so ambiguous? They're just mathematics to get the equations to stabilize. Virtual particles. What are these virtual particles? You'll have people telling you that in the vacuum of space you have particle antiparticle pairs popping in and out of existence spontaneously, and the particle antiparticle pair just pops into existence spontaneously and then disappears, recombines, and the net result is zero. What exactly is the deal with these virtual particles? Are these just mathematical tricks that we use to balance things out, or what exactly is this? So here's the deal. The best theory of the ultra microscopic quantum world that we have is quantum field theory. We have quantum mechanics, we have quantum field theory. So quantum field theory comes from second quantization. I will not go into all the details, but quantum field theory says that the universe is basically fields. Fields, not particles, fields. But what about the particles? We have electrons, we have protons, we've got neutrons, we have quarks, up, down, top, bottom, strange, charm, six generations of quarks. We have all kinds of other particles. We have particles, so why are you saying there are only fields? So quantum field theory says that these particles are merely localized excitations in the fields. So there is a field, just one electron field that permeates the entire universe. And in certain parts of the universe, in certain locations, there are excitations in the fields. And those localized excitations are what we consider to be particles. Similarly, there's a single photon field across the entire universe. And localized excitations of the photon field are what we interpret as photons. Similarly, for the quarks and all the other particles. So it's just fields, all across the place, all across the universe. And these fields, some of these fields interact, some of these don't interact, etc. So that's the first concept we have to understand, that the universe is actually made of fields. And this is the best quantum theory that we have, quantum field theory. Okay? Probably one of the most successful theories of physics that we have. I mean, we explain everything through that, and it really works. So the entire universe is just fields, all these particles, etc. It's just illusion. It's just Maya. Okay. Now, what if a field in a certain region of space has zero energy? No energy whatsoever. Absolute zero energy. What happens? It would mean that there are no excitations in the field. There are no localized excitations in the field. That's what it would mean. But here's the deal. In quantum mechanics, even the lowest energy state of a field is not free from what we call quantum fluctuations. There are still what we call 0-point fluctuations at the lowest energy state of a field. 0-point energy, which means that even when a field has zero energy, it still has these persistent vibrations, fluctuations, whatever you want to call it. It's still restless, right? And these 0-point quantum fluctuations, that is what we call virtual particles. So you have a localized quantum fluctuation that can be represented as a particle-antiparticle pair briefly coming into existence out of vacuum and recombining before we can offend Dr. Heisenberg. Heisenberg's uncertainty principle. You operate within the bounds of that. You create the particle-antiparticle pair and have it annihilate in such a small time window that it doesn't trigger or trip the Heisenberg uncertainty principle. Right? So that is the deal. So you could consider it to be mathematical artifacts, but it's not just mathematical artifacts or mathematical tricks or whatever you want to call it. These 0-point fluctuations, quantum fluctuations, do exist. And there is experimental evidence of that. The Casimir effect and whatnot. You can look at what those things are. And these quantum fluctuations, okay, they have always been around. They were around in the very early universe, when the universe was like this size. So those very early quantum fluctuations in that incredibly compressed universe, what did they end up doing? Those little quantum fluctuations created overdensities of matter in very, very small areas of the universe. And when the universe is so incredibly compressed, a tiny quantum fluctuation can create a micro black hole. Which is why it is highly likely that in the very early universe, you had an overproduction of primordial microscopic black holes. And in other eras or epochs of the universe, also like reheating, etc., you had possibly an overproduction of primordial black holes, micro black holes. So that's what these virtual particles are. Are they super luminous? They don't have luminosity because they disappear before you can even think of their existence. But overall, they give rise to actual measurable physical effects. Why are they called virtual particles? You can call them whatever you want, but that's what virtual particles are. It's not just mathematics, it's actual quantum mechanical effects. All right. Let's talk about black holes. Advait Ashwini says, what is the no-hair theorem and how is it related to black holes? The no-hair theorem. So what is this hair in the no-hair theorem? The no-hair theorem says black holes have no hair. So when we talk about hair in this context in physics, in black hole physics, hair is just a slang term, which means extra details. What extra details? When you see a star, when you see the sun, we know it has mass. We know it has angular momentum because it rotates. It has magnetic fields. It has solar prominences. It has sunspots. It has various other effects. It gives off solar wind. It has all these little details that together characterize what the sun is. All kinds of small extra details, right? But when it comes to black holes, the no-hair theorem says that a black hole, when seen from outside the event horizon, has only three properties: mass, charge, angular momentum. Mass, charge, angular momentum. Everything else, the so-called hair, isn't there. Just three properties can completely and fully describe a black hole's entire set of properties. Everything about a black hole: mass, charge, angular momentum, that's all you need to describe it. So that way it has no extra hair. That's what the no hair theorem means, right? And that's how it's related to black holes. So look, the simplest black hole is a black hole that only has mass, pure mass, no charge, no spin. What is angular momentum? Spin. Wait, this one. Yeah, this is more like a black hole. So a black hole, if it is rotating around its own axis like this, spinning, so that's a black hole with spin, and that's a black hole with angular momentum. So the simplest black hole is an uncharged massive black hole that is not spinning. That's called the Schwarzschild black hole. Then you also have two other kinds of black hole. One is a spinning, rotating charged black hole. The other one is a non-rotating charged black hole, which obviously both these kinds of black holes have mass. So that's all it takes to describe the properties of black holes. Everything you need to know about a black hole, these three properties describe it, which is very strange. Very strange, right? Because what happens to all the other little details that go into a black hole? For example, let's say I create a black hole. Okay, this is a thought experiment. I take a tremendous amount of hydrogen gas and I compress it together until it becomes a black hole. So I will have a black hole, right? Which was made of initially just hydrogen gas. Now let's say I have a neutron star. See, when a star dies, various things can happen to a star. It can either, like our sun, eventually become a red giant and then the outer layers just blow away into a big planetary nebula kind of thing, like the Cat's Eye Nebula. And then at the core, what's left behind is what's called a white dwarf, which over billions or trillions of years will become a black dwarf. So that's one possible end of a star. The second possible thing that can happen to a star is it becomes a neutron star. The third possible thing that can happen is it becomes a black hole. So if you have a white dwarf, it has a maximum possible mass, 1.44 solar masses, which is the Chandrasekhar limit. That's the maximum mass of a white dwarf. Beyond that, you will have neutron stars. Okay? So a neutron star also has a maximum limit, which is the Tolman-Oppenheimer-Volkoff limit. So that is what 2 point something solar masses. You can look it up what the exact figure is. Let's quickly look it up. Tolman-Oppenheimer Volkoff limit. What is it? 2.9 or something solar masses. Over here it says 2 to 3 solar masses. I think it's about 2.8 or 2.9 solar masses. Okay. So let's say I take a neutron star, which is right at the edge of the limit, right at the edge of the Tolman-Oppenheimer-Volkoff limit. And I take a teaspoon of sugar and I dump it into the neutron star. What's going to happen? It's going to exceed the Tolman-Oppenheimer-Volkoff limit, and the neutron degeneracy pressure will be overcome by sheer gravity, and it's going to collapse into a black hole. Into the smallest black hole stellar mass black hole you can have, which is about roughly 3 solar masses. Okay? So I can create a black hole out of a neutron star by putting a teaspoon of sugar into it. Now, this neutron star was complicated. It was complex. It had an iron plasma atmosphere, maybe 1 millimeter thick. It had a crust made of exotic nuclei. It had an inner structure that was increasingly more complex as you go inwards towards the center. Near the center, you will have nuclear pasta, which we don't even understand properly. All of this tremendous detail, it just got squashed into a black hole. And now all the details are gone. All you have is mass, charge, angular momentum. And if you take the same amount of hydrogen gas, 1 teaspoon of sugar more than the Thorman Oppenheimer Fokoff limit, and then you squeeze it into a black hole, you will have the exact same black hole. Same mass, same charge, same angular momentum. But you form these two through totally different means. Right? So what happened to all that fantastic information? The information about the hydrogen atoms, their spectra, whatnot. And what about all the complex details of the neutron star that became a black hole? All the details disappear. So yeah, that's the no-hair theorem, and I'm actually talking about something else also, which is the black hole information paradox, which is a totally different matter. So anyway, that's the no-hair theorem. A black hole can only be described by 3 parameters: mass, charge, angular momentum. Everything else, like the radius, is a factor of these things. The radius of the Schwarzschild radius of a black hole is given by R equals 2mg by c squared. mg c squared. G is just Newton's universal constant. So you have m and c, which gives you, c is the speed of light. So mass gives you the radius. Anyway, mass, charge, and angular momentum. Ritik Pawar says, what would happen if a 10-kilometer diameter black hole passed near Earth's orbit? Scary stuff. Black hole, only 10 kilometers in diameter. What will happen if it passes near Earth's orbit in the solar system? Now, first of all, let's try and calculate the mass of this black hole. 10 kilometers diameter, which means 5 kilometers radius, right? So this black hole, which we are talking about, has a 5-kilometer radius. Let's ask ourselves, what is the Schwarzschild radius of the sun? Which means if you take the entire sun, you squash it somehow, and turn it into a black hole, what will be the radius of the black hole? It turns out it's about 3 kilometers. Roughly 3 kilometers. Let's fact check that. Schwarzschild radius of sun. Excuse the spelling, but it's approximately 3 kilometers. There we have it. So if you have a black hole with 5 kilometers radius, it's going to have a mass roughly double the sun. Roughly, okay? Let's say it's roughly twice the mass of the sun. So you have an object which is twice as massive as our sun, but it's only 10 kilometers in diameter. Imagine that, how shocking that is. That's how much mass is compressed into this object, this black hole. Now let's say this black hole tragically enters the solar system and passes near the Earth's orbit. What will happen? So what's the Earth-Sun distance? The Earth-Sun distance is called 1 astronomical unit. So let's say we have the sun sitting here. The Earth is going around the sun at this distance. And let's say the black hole, so the Earth is here, okay? Over here. But the black hole with 10 kilometers diameter, it comes from here, this direction, passes from here, at a distance of 1 astronomical unit from the sun, okay? From here. And the Earth is here. So it doesn't come right next to the Earth. The Earth is here, but the black hole comes from here, at the same distance from as the Earth and the sun distance. So when the black hole is behind the sun as seen from Earth, then the Earth will experience way more gravitational pull than what it does. So what will it do? And this is the best case scenario. Because the Earth will suddenly experience almost double, less than double, but let's say double, hypothetically, for the sake of argument. Let's say the Earth experiences almost double the gravitational pull than it usually does. What it will do is that it will totally warp the Earth's orbit. It will elongate the Earth's orbit significantly. It will become way more eccentric than what it is right now. The Earth has an elliptical orbit, not a circular orbit around the sun. The Earth's orbit will be warped significantly. It will end up having a much more elongated orbit around the sun. So it will come closer to the sun at the nearest approach, which will fry the side of the Earth that faces the sun, boil away the atmosphere and whatnot. Even if that doesn't happen, after passing near the sun, the Earth will go in a very long, elongated orbit, maybe all the way to Neptune's orbit, maybe Pluto's orbit. And that orbit will take a couple of 100 years, maybe. So right now, one pass around the sun takes us 365 days. If a black hole comes and does this maneuver, maybe one orbit around the Earth, around the sun for the Earth, will now take 200 years. And most of the time, Earth will be far, far from the sun, which means it will be frozen solid minus 150 degrees, minus 200 degrees for about close to 200 years. And then it comes close to the sun and everything just melts and burns. That is the best case scenario. What does it mean? It means the end of life on Earth. That's the best case scenario. Now let's say we have the sun here, we have the Earth here, and the black hole comes from somewhere here. Maybe the black hole comes within, let's say 10 million kilometers of the Earth. Let us just quickly fact check what is 1 astronomical unit in kilometers. 1 AU in kilometers. So 1 astronomical unit is about 1.5 times 10 raised to 8. 150 million kilometers is 1 astronomical unit. So instead of 150 million kilometers, let's say it comes 15 million kilometers from the Earth. What happens then? So this is a much more drastic event for us now. What it will do if it comes so close to the Earth is it will exert tremendous tidal forces on the Earth. See, we experience tidal forces in a very gentle way. We have the Earth, we have the moon going around the Earth, and the passage of the moon, wherever it passes, it exerts tidal forces on the Earth, which means that the oceans bulge out. And because of that, we have high tide and low tide in a gentle way on the planet. Nothing drastic. But now we have this monstrous black hole, twice as massive as the sun, passing 15 million kilometers, or 1/10 of the Earth-Sun distance from the Earth. What will happen? The oceans will bulge out all the way. The Earth's crust will get distorted. Tectonic activity, the Earth's crust will distort. It'll snap. It'll crack. You will have magma coming out of the Earth. It's like a million Yellowstone super volcanoes going off all at once. The atmosphere could burn or could be sucked out into space towards the black hole. And the Earth will once again be a lava planet. Absolutely hellish lava planet. Just like it was about 4.5 billion years ago when the Earth had just formed. So the Earth, its crust will be broken. All the lava magma will ooze out. The Earth will become elongated like a rugby ball. And once the black hole passes, the Earth may resume its spherical shape, but it will be back to like the situation which you had 4.5 billion years ago when the Earth had just formed. It was a hellish landscape, a molten planet. That's what you will have if the black hole passes about 15 million kilometers from the Earth. What if the black hole passes the same distance as the moon from the Earth? Third scenario. This is when the Roche effect comes into play. Why does Saturn have rings? Because one of Saturn's moons came too close to Saturn. And it came so close to Saturn that the gravitational pull on one side of Saturn's gravitational pull on one side of the moon's surface was so much stronger than the other side that the moon just crumbled and was ripped into pieces. And that's what formed the rings of Saturn. Saturn. Now, if a black hole comes within Earth-Moon distance to the Earth, it's gonna do that thing to Earth. It will simply shred the Earth into spaghetti. So Earth will become a long string of lava and magma. Some of it will be sucked into the black hole. So it won't go straight into the black hole. It will form an accretion disk, like Saturn, a molten, glowing accretion disk, which over months or years or decades will be completely absorbed by the black hole. And some of Earth will be left behind. Some of it will be flung into space, never to return. And some of it will be left behind, which may recoalesce into a much smaller planet. And obviously, once again, this is an extinction event, nothing survives. So, all three scenarios, life is destroyed on the planet. And this is what we talk about what happens to the Earth, right? But if a black hole were to pass through the inner solar system, it will mess up the orbits of all the planets. And the entire solar system will be reconfigured drastically. It will be unimaginably altered forever if a black hole just zips through the inner solar system like 3I Atlas or Oumuamua or whatever else. It may even, hurt the sun. It may even do something bad to the sun. So these are the different scenarios that could ensue if a black hole passes through the inner solar system reasonably close to the Earth's orbit. Pretty scary scenarios. And in none of the scenarios does any life survive on the planet. Advait Ashwini says, we know black holes are majorly described by three properties: angular momentum, charge, and mass. But if a black hole is charged, where does it store this charge? Does it store the charge on the surface of the black hole, or does it store the charge inside the black hole? If it's on the surface, then how is it just empty space on the outside? Okay, before I begin to answer, what is the surface of a black hole? Does a black hole have a surface? Well, the surface that we talk about for a black hole, it's what we call the event horizon. It is an imaginary surface. It's not a physical surface with flag over there. Hey, you're passing the event horizon. No such thing. If you are an astronaut, an unfortunate astronaut, and you're falling into a black hole, when you cross the event horizon, you will feel nothing at all. You will feel nothing special once you cross the event horizon. You will not even know that you crossed the event horizon. So it's not a real surface. It's not a physical surface that you can touch or feel. It's not a membrane that you pass through and you feel it. It's just a causal boundary. Once you cross that invisible imaginary boundary, there's no way you ever come out. That's the event horizon. And that's the surface of a black hole from our intents and purposes from outside. Okay? Now the question, where is the charge of a black hole stored? Right? Where is it stored? See, let's say I have a copper ball, which has a, let's say, net negative charge. Okay? So how do I know this copper ball? Imagine this is a copper ball. You get the point. So how do I know this copper ball has X amount of negative charge? How do I know it? Do I open the copper ball and look inside how many electrons are there? Do I count the electrons? Of course not. I don't count the electrons. What you do to measure the charge of a copper ball is you bring a small test charge near this copper ball and you measure the electric field near the copper ball. That's what you typically do. That's how you measure the charge of a copper ball, iron ball, whatever ball, of any charged object. That's how you measure its charge. And the same goes for black holes. Let's say I have a charged black hole. Let's say I have a black hole and I want to measure the charge. So I could bring a probe near it and measure the electric lines of force. I mean, do the same thing I would do with a copper ball. You can use Gauss's law. The electric flux coming through the surface, through any Gaussian surface, is an indicator of how much charge the surface contains, that sort of thing. So based on this understanding, if you are an external observer who is fortunately not inside the black hole, then from your perspective, the entire charge of the black hole is present on the surface of the black hole, this imaginary surface called the event horizon. So if the black hole has a net charge, all of that charge is smeared on the surface of the black hole. The surface is like a perfect conductor of charge, perfect conductor of electricity. Yeah, that's how we see it from outside. But actually, what's the deal? Well, if you look at Maxwell's equations, you solve Maxwell's equations, it will tell you that the electric lines of force, they go all the way inside the black hole, all the way to the singularity. But does it mean that that's an actual singularity inside the black hole? And does it mean that the singularity contains the charge? Not necessarily. We don't quite know what's inside a black hole. This is just what Maxwell's equations tell us, and Maxwell's equations don't know about black holes. Right? So for all intents and purposes, the charge of a black hole is smeared on its external boundary, which is this imaginary boundary called the event horizon. Now, what if I shoot an electron or a stream of electrons? Let's say I shoot a stream of X number of electrons at the black hole. So then the black hole's charge will increase. It already has charge Q, and I'm going to shoot X electrons. Each electron has an electron's charge. So the black hole's charge eventually should become Q, the original charge, plus X times the electron charge. So what happens to this extra charge that arrives at the black hole? The electrons are going to be absorbed by the black hole, right, inside the event horizon. And yet, the effect is going to be such that all that charge carried by the electrons is going to get smeared on the surface of the black hole. Right? So, yeah, that's about it. So, from an external observer's perspective, the charge is going to live on the surface of the black hole. That's it. Yajnavalkya says, from the perspective of an outside observer, a black hole never forms, since any object, be it the collapsing star or anything else, outside the black hole should take an infinite amount of time to reach and constitute the event horizon. So did LIGO not actually detect a black hole? And do we actually not have a picture of a black hole? Also, black holes supposedly should evaporate through Hawking radiation in a finite amount of time. So from the perspective of an outside observer, does a black hole evaporate before it can even form? Interesting questions. So what happens? So first of all, let's do this thought experiment. I have a black hole sitting here, and I have a poor, unfortunate guy who is falling towards the black hole. Okay? Space astronaut wearing a spacecraft, wearing a space suit, sorry. An astronaut wearing a spacesuit is falling towards the black hole, and I am far away watching what's happening. I can't help him. If I try to help him, I'll also join him in this journey. So I stand outside and I'm just watching my colleague drift towards the black hole, get pulled towards the black hole. So what do I see? The closer my colleague goes to the black hole, the slower he seems to be going. From an external observer's perspective, the infalling astronaut goes slower and slower and slower until he or she essentially freezes, stops moving just outside the event horizon. And then the image of the astronaut gets dimmer and dimmer and dimmer and dimmer and dimmer until it disappears. You never see the astronaut enter the event horizon and disappear inside. The person just freezes. The image of the person freezes outside the event horizon, and it then starts getting dimmer and dimmer and dimmer and eventually disappears. That's what we see. Why is that? It's because of relativistic effects. So it gets dimmer and dimmer because the photons get more and more red shifted because they have to expend more and more energy to get out of the gravitational well of the black hole. And the slower and slower thing is because of time dilation. So because of these effects, you will find that you will never observe anything fall inside a black hole. But if a star is collapsing into a black hole, then we should see the same thing, right? You should never see the star actually go within the event horizon, which means that if I'm sitting outside, I should never see a black hole form ever. What is the deal? Right? See, You will never see a black hole form because black holes are invisible. They're not black. They are not black. A black hole is not a black object. It's invisible. So if a star collapses into a black hole, you may see the star's light getting, freezing right outside the event horizon, and then the star will become dimmer and dimmer and dimmer until the star becomes invisible, which tells you the black hole has actually formed. Now, the reason why there is this conception, this misconception that it takes an infinite amount of time to form a black hole is because of a coordinate artifact. See, black holes, who discovered the equation? How were black holes discovered? Einstein came up with general relativity in 1915, and this was in the form of the Einstein field equations. And Einstein thought it will take several decades before anybody can solve the equations. But just a few months later, an astronomer named Karl Schwarzschild, who was on the front lines of the First World War, in the trenches, in his free time, he solved the equations and he sent them to Einstein. He died a few months later, sadly. So this was the Schwarzschild solution of the Einstein field equations, and that's what told us that black holes exist. But the coordinates that Schwarzschild used to solve the Einstein field equations, which are now called the Schwarzschild coordinates, they contain two singularities. One is the singularity at the heart of the black hole. The other singularity is at the event horizon. But that's not a physical singularity, it's a coordinate singularity. If we use Eddington-Finkelstein coordinates or some other coordinates, the singularity at the event horizon vanishes. So it's just a mathematical artifact. But that gave rise to the misconception for decades that it takes an infinite amount of time for a black hole to form, which is not the case. Okay? So you may see from outside, it may appear to you from outside that something that's falling inside a black hole never reaches the black hole. It just becomes invisible eventually after a very long amount of time. And if a star is collapsing, it may seem to you that the star stops colliding right outside the event horizon phase. And then it simply slowly dims and eventually disappears after a very long amount of time. But it's just what you are seeing from outside. If you have the astronaut falling into the black hole and he or she is carrying a clock, the clock will be ticking absolutely normally for him. But for you from outside, it will look like his clock, the astronaut's clock, has stopped. So that's why it's called relativity, because two observers will not agree on what's happening. Right? So it does not take an infinite amount of time for a black hole to collapse. When a star collapses into a black hole, it typically takes milliseconds for a full star to suddenly collapse into a black hole. The collapse happens at such high speeds that they are close to the speed of light. In milliseconds, the star is gone, winked out of existence. Maybe a second or two at most. That's how fast the collapse happens. Okay? So black holes. So the question is, did LIGO? So black holes exist. They form in real time, very short amount of time, and we have a picture of a black hole. LIGO did actually detect merging black holes, etc. Now about black hole evaporation. Black holes evaporate in a finite amount of time. There's a certain rate at which a black hole evaporates, which depends on its mass and temperature. Temperature is a function of mass. dm by dt is equal to minus k upon m squared. You can look it up. Yeah, dm by dt is the rate of change of mass. Is minus means it's evaporating, not plus. So dm by dt is minus k is a constant divided by m squared. So it's inversely proportional to the square of the mass. So the larger the mass, the slower the evaporation. The smaller the mass, the faster the evaporation. Essentially, that's what it is. So black holes evaporate through Hawking radiation in a finite amount of time. So from the perspective of an outside observer, the black hole evaporates before it can even form. So like I said, black holes do form. They don't take an infinite amount of time to form. But let's say a black hole, hypothetically, for the sake of argument, takes an infinite amount of time to form. Then how will it evaporate? How will it start evaporating before it becomes a black hole? It can't. A star is collapsing. Let's say it takes infinite amount of time for a star to become a black hole. Then how will the star begin to evaporate before it becomes a black hole? It's impossible, right? Only black holes evaporate, stars don't. Only black holes evaporate, neutron stars don't, etc. So I think that doesn't make logical sense. It has to first become a black hole, only then can it evaporate. Otherwise, there can be no evaporation possible. But the main thing is that this is a misconception that black holes take an infinite amount of time to form. They take milliseconds to form. When a star, when the floor, when the bottom falls off beneath a star, once the electron degeneracy and then neutron degeneracy pressure collapses. When gravity overcomes these two forces, it's game over. It takes milliseconds for a star to become a black hole. Surya Pratap says, why are all suns made up of hydrogen? When you say why are all stars made of hydrogen? These stars will use whatever's available to them. What is the most abundant element in the universe in terms of mass? Hydrogen. About 75% of the baryonic mass, non-black hole mass, non-dark matter mass of the universe is hydrogen. 75%. About 24% probably is helium. And the rest is everything else. Okay, let's just double check that. What is the hydrogen helium composition of the universe? What is the hydrogen and helium percentage composition of the universe? Okay, what's it say? So 75% is hydrogen, about 25% is helium. Yeah, by mass. Number of atoms, 92% hydrogen, 8% helium. So about 75% of the mass is hydrogen, 24% is helium, and 1% or less is everything else. Oxygen, lithium, carbon, nitrogen, silicon, iron, uranium, gold, whatever. All of that is less than 1%. So when that's what the universe gives you, that's what you use, right? So that's the primary reason why all suns are made of hydrogen. See, what is a sun? What's a star? It's a gigantic fusion reaction. The universe, when it was formed, initially was just tremendously massive, tremendously dense. Eventually, you had protons and neutrons and electrons buzzing around, but the universe was still so hot that they could not combine. There was a brief amount of time when the universe was expanding, when the universe acted like a gigantic fusion reactor. Okay, for a very brief amount of time. That's when you had protons and electrons coming together and forming hydrogen nuclei, and also sometimes protons and neutrons coming together, one proton, two neutrons, to form helium nuclei, and then they would combine with electrons to form atoms. But before this process could continue to heavier elements, the universe became larger, it expanded and cooled. So the fusion reaction turned off. So what we were left with was hydrogen, about 75%, helium, 24% or so, a little bit of lithium, and that's about it. So the very initial stars, which formed because of regions of density in space, which came out of primordial quantum fluctuations, the very initial stars only had hydrogen and helium. So these gas clouds would come together and collapse under their own gravity. And eventually the mass would be so much and the pressure would be so much that a fusion reaction would ignite at the center, and the fusion would be mostly hydrogen nuclei fusing into helium nuclei, and that gives off a tremendous amount of energy, which is why the stars are able to repel the gravitational pressure and keep burning for billions of years. Eventually you had multiple generations of stars, so the initial stars eventually died. Some of them went supernova, etc., and that gave rise to heavier elements, and that's how you had the seeding of other elements in the universe. So that's why overall stars are mainly, even today, made of hydrogen. Our sun is mostly hydrogen, little bit of helium, 75% hydrogen, 24 or so percent helium, and whatever else is the rest, right? And obviously another reason is that hydrogen, the fusion of hydrogen, gives off the most energy you can imagine and takes the least amount of energy to ignite. See, hydrogen has just one proton at the center. And if you want to fuse hydrogen into helium, it takes a certain amount of energy. But if you have more protons and neutrons, etc., in the center, it takes way more energy to fuse heavier elements together. That is why all fusion reactions in stars start with hydrogen fusing into helium. Then you have fusion of helium and other heavier elements. Eventually, you will have lithium, oxygen, lithium, carbon, oxygen, etc., higher and higher things, silicon, and it all ends when the star starts fusing, producing iron. Iron is the nuclear ash that is the death sentence of a star. Because if you try to fuse iron into something heavier, it's possible, but the reaction consumes more energy than it gives out, which means it kills the star, which is why all the iron that we have here came from the death of stars. Anyhow, that's why all stars are made of mainly hydrogen and helium. Ayush Singh says, the gas giant planets, don't they have surfaces like the Earth? If we were to send a rover to those planets, where will it possibly land? Why don't these gas giant planets have surfaces while the Earth does have a surface? What was different which created such a beautiful surface on our mother planet? Okay, gas giant planets such as Jupiter and Saturn. And you also have ice giant planets like Uranus and Neptune. So what's the difference? Gas giant planets like Jupiter and Saturn are mainly made of hydrogen and helium. And ice giants like Uranus and Neptune, they have water, they have methane, they have ammonia. They also have hydrogen. So that's the difference. Now let's talk about something like Jupiter or Saturn. Mainly made of hydrogen and helium. Very similar composition to the sun. So let's take the example of Jupiter. When we see an image of Jupiter, all those beautiful bands and clouds and all, what is that? That's the very highest layers of the atmosphere, which is mainly hydrogen gas. That's very thin and very cold. So let's send a probe inside, a spacecraft. We have started skimming the surface of, not the surface, but the very top layers of the atmosphere, which is what we see in the images, with all those beautiful bands and all that. That's very thin, very cold. Then we go deeper into the atmosphere, deeper. So then the atmosphere gets thicker and warmer. Eventually, as you go deeper, you will have thicker and thicker layers of hydrogen gas, and they get warmer and warmer, and the pressure gets higher and higher. Eventually, you will reach a level in the atmosphere of Jupiter where the air pressure is similar to the air pressure on Earth, and temperatures could be possibly similar, and it's all hydrogen. Go further inside, and the gas gets thicker, the pressure rises significantly, it gets warmer and warmer and hotter. So after one Earth atmospheric pressure, you go deeper, you will have two atmospheres, 3 atmospheres, 10, 20, 100, several hundreds, thousands of Earth atmospheric pressures. Eventually you will reach a region of the planet Jupiter where the hydrogen gas will no longer be gaseous. It will be a supercritical fluid. Let's call it liquid hydrogen. It will be what is actually called a supercritical fluid. It is no longer gaseous. You could think of it as a liquid, and it's really dense. The pressure is intense, immense, and it's really hot. You go further and further inside towards the center. Eventually, you will reach a stage or a depth in the planet where you have metallic hydrogen. So this is hydrogen at a tremendous pressure and temperature, where the hydrogen atoms taken together behave like a metal. They conduct electricity. And this is where Jupiter's tremendously powerful magnetic field comes from. But here also, you don't have a surface. It's just getting hotter and denser, and the pressure gets higher and higher. Eventually, at the very core, You may perhaps have some rocky aspect, which is the rocks and asteroids and whatever else Jupiter has absorbed, swallowed over the millions and billions of years, and that's about it. It may perhaps, there are some theories that says that Jupiter may have a carbon crystal center. What does it mean? Diamond center, core. It's possible, but we're not for sure. We don't know for sure. But that's about it. So there is no actual surface where you can stand. If you send a probe inside Jupiter, okay, a rover or a probe, eventually it will just melt or get crushed, but it will never find a surface to stand on, even all the way to the very end. So if you want to explore Jupiter, for example, what you can do is you can send a spacecraft either on a final mission, which it knows it won't survive. It will be like a meteorological observatory, which will take readings at various depths until as long as it survives. Readings, and it will send back maybe data to the Earth, whatever it's able to send back. Another thing we can do is we can send a spacecraft that is designed like an airship, like a balloon. Let's say we design the aircraft, the space probe, to be able to float in Jupiter's atmosphere, let's say at one atmospheric pressure of Earth. So it will float at that height, and it can stay there for years if you design it right. So that's another way of doing it. Or you can send a spacecraft and have it land on maybe Europa or one of the Jovian moons, from which it can take observations and data from Jupiter. So that's what we can do. But as such, Jupiter and the gas giants, whether it is Saturn or whether it's the ice giants like Neptune or Uranus, they don't have a surface that we can think of as a surface. See, on Earth, we have a very clear boundary. We have land, and then we have the air, atmosphere, or we have ocean and atmosphere, very clear dividing line. On the gas giants and ice giants, we don't have that. It's just the property of those, it's just the inherent property of these planets. So what is different about Earth? Because we are a rocky planet. We have so much rock, which is how we are fundamentally different from the ice giants and the gas giants. Surya Pratap says, when Mars was a habitable planet, what would have been the condition of the Earth at that time? Were dinosaurs roaming on the Earth during that period? Okay, so chronology, let's see. The solar system forms about 4.6 billion years before today. Okay, there was the formation of the solar system. Our planet, Earth, it formed about 4.56 billion years before today. And when it formed, it was this hot, hellish, molten lava, molten magma planet, which over time cooled, solidified. You had the Helium epoch and whatnot. Very different kind of planet it was at the time. Mars also formed during a similar time as the Earth, similar time period. Now, when was Mars habitable? What do we mean by habitable? What we mean by habitable is that Mars had a warm, thicker atmosphere than it has today, and it had flowing water on the surface, rivers, maybe oceans on the surface. And it had precipitation either in the form of rain or snow or whatever else. So that is what we mean by habitability. Flowing water, thicker atmosphere, and precipitation. So when was this? When was it the case that Mars fulfilled these criteria, habitability? That's between 4 billion years before today and 3 billion years, roughly 4.1 billion years before today to 3 billion years before today. That is the time window, roughly, give or take, during which Mars was habitable. Okay, so what was the Earth like at this time? The Earth was very different 4 billion years ago. Earth's atmosphere was tremendously different, mainly carbon dioxide and nitrogen and water vapor, and maybe some other gases. Very little oxygen on Earth at the time. The earliest unambiguous evidence of life on our planet is from 3.77 billion years ago, the first bacteria. About 3.5 billion years before today, on our planet, we had these bacteria that formed mats and colonies whose fossils still exist. Chromatolites, they're called. let us quickly take a look at what these stromatolites would have looked like on our planet. Stromatolites. Oopsie daisy. Okay. So what do these things look like? See, these are the fossils of these ancient stromatolites from about 3.5 billion years before today. We still find them along coastlines, etc. Stromatolites, fossils of the earliest life on Earth. And it's possible that these were our ancestors. So 3.5 billion years before today, on our planet, we had these bacteria. And that was the only life on the planet, all microorganisms, microscopic life. That's the time period when Mars was a habitable planet. When did the first dinosaurs emerge? Roughly 250 or 270 million years before today. Mars was long dead by that time. Okay? So dinosaurs were not roaming on the Earth during the time when Mars was habitable. You only had microscopic, unicellular, mostly life on our planet at that time. Advait Ashwani says, why can't we put more neutrons in a nucleus after a certain limit? Good question. So, we have something. See, what's a nucleus, atomic nucleus? It's where you have protons and neutrons. And around the nucleus, you have a cloud of electrons. Not in a solar system style, but in a probabilistic smeared out manner. Okay? So in the nucleus of an atom, we have protons. The simplest nucleus, let's talk about it first. It's the hydrogen nucleus. It's a single proton. Then you have helium, which is 2 protons, 2 neutrons. Yeah, 2 protons, 2 neutrons. That's the standard helium nucleus. See, protons are positively charged. And we know that like charges repel each other. So if you take 2 positive charges, bring them together, they will repel each other very strongly. So how do we bring 2 protons together in a nucleus? How do we make it happen? How does nature make it happen? There is something called the strong nuclear force, which is a very powerfully attractive force. So that is one factor. You take 2 protons together, they have this electromagnetic repulsion, which is very strong. But there's also the strong force attraction, which counteracts the electromagnetic repulsion. And when you bring in neutral particles like the neutron into this mix, then the strong force has the effect of stabilizing the nucleus and counteracting successfully the electromagnetic repulsion of the positively charged protons. So you bring protons together, but you have to add neutrons also to have an effective amount of nuclear attraction from the strong nuclear force that binds the nucleus together. So the more protons you put in a nucleus, the more neutrons you have to add to have the nucleus remain or become stable. Right? So that should mean that you should be able to keep adding protons indefinitely as long as you add more neutrons. But that doesn't work out. There is something called the neutron drip line. Neutron drip line. So what happens? First of all, before we discuss the neutron or nuclear drip line, this is what happens. The strong nuclear force is very strong, but it only acts at a very, very short distance. It is a very short range force. So it will act very strongly on 2 nucleons. That is, what is a nucleon? Proton and neutron are called nucleons. 2 nucleons together, the nuclear strong attractive force is very powerful. But the more nucleons you add at the very edges of the nucleus, the strong force becomes weaker than at the center. Okay? And eventually, if the nucleus is large enough, if you add 1 more neutron, it will simply drip off. It will simply drip off. And that limit is called the nuclear drip line or the neutron drip line. Let's see what it looks like. It's a graph. Okay? Drip line, neutron drip line. And yeah, so you have, stable nuclei in the drip line, etc. 2 neutron drip line, 2 proton drip line. So there are these limits in nuclear physics that we talk about. Okay, so one reason is this, that the strong nuclear force, despite being incredibly strong, is a short range force. So if you have a large nucleus and you keep adding neutrons to it, then eventually the strong nuclear force becomes not strong enough. It is no longer strong enough to have additional neutrons stick to the nucleus. They just drip off. That's one. Number two is something called the Pauli exclusion principle. Now, there are various humorous ways of describing it, which I will not do here, not the right setting. But the Pauli exclusion principle is the reason why matter has mass. So it's the reason why matter occupies space. What does the Pauli exclusion principle say? First of all, there are two classes of particles, of subatomic particles: fermions and bosons. Fermions, they obey something called Fermi-Dirac statistics, and bosons obey something called Bose-Einstein statistics or Bose statistics. Protons, neutrons, electrons are fermions. They obey Fermi-Dirac statistics. And forget about what all that is. The Pauli exclusion principle says that for fermions, no two identical fermions can occupy the same quantum state. So protons come in two spins, spin up, spin down. It's like one is off spin, one is leg spin. All right, that sort of thing. It's not exactly that, but let's think of it that way. So protons come in these two spins. So in any one quantum state, you can only have a spin up and spin down proton. You can't have a third proton in there. And because of that, there is a limit to the number. So think of the atomic nucleus as a stadium. In the stadium, you have the bottommost, cheapest seats. Then you have a higher level of seats, which are more expensive. Then you have a higher level is more expensive. Eventually, you have the most expensive seats. Initially, you want to fill all the lowest seats, right? So you fill them up. Then you fill the higher energy seats. Cost is energy. Higher energy seats. Then higher energy, higher energy. Eventually, there will be a limit beyond which, if you want to add a proton or a nucleon, it simply becomes too energetic to remain in the nucleus, essentially. And it makes more sense for the nucleus to kick that proton out or nucleon out than to keep it within the nucleus. It becomes like this extremely hyperactive, high energy gas that you don't want. So it just makes sense for the proton to kick for the nucleus to kick that nucleon out of the nucleus. Another thing that the nucleus can do sometimes is it can simply transform a neutron into a proton through beta decay. It's a nuclear process which involves a weak nuclear force, which is one of the other forces as opposed to the strong nuclear force. So if you have too many neutrons, it simply transforms a neutron into a proton and kicks out an electron. So eventually there's a limit beyond which neutrons simply won't fit into a nucleus, and they'll simply drip out because of and that's the nuclear or neutron drip line. So because of the short range nature of the strong nuclear force, because of the process of beta decay, which is something the nucleus does whenever required, and because of the Pauli exclusion principle, because of these three factors, there is a limit to which you can add neutrons into a nucleus, beyond which it simply won't work. Rahul Dunake says, is there a possibility of discovering a type of radiation more energetic than the gamma rays? Can the electromagnetic spectrum increase at both ends? Great question. See, gamma rays are photons. Radio waves are photons. They are on two different ends, essentially, of the electromagnetic spectrum. But these are not different species of spectrum of protons of photons. Gamma rays and radio waves are not different species of photons. They are simply photons. We use these tags, these titles, to depict photons of specific frequency or energy ranges. But it's not like these are different kinds of radiation. These are all photons. Let's take a look at the photon energy range, shall we? photon spectrum. How about that? Which is the electromagnetic spectrum, actually, but let's just call it the photon spectrum. Let's see the first one that we have here. So gamma rays are extremely high frequency photons, high frequency, short wavelength, and they are emitted by very high temperature objects. Okay. Excuse me. And at the other end of the spectrum, you have radio waves, which are very low frequency photons with very long wavelengths. So for a radio wave, a typical wavelength is about 10 raised to 3 meters, which is what? 1 kilometer wavelength. And the frequency is about 10 raised to 4, 10,000 cycles per second. For a gamma ray, the typical wavelength is about 10 raised to minus 12 meters, and the frequency is about 10 raised to 20 or more cycles per second. So these are the two ends of the electromagnetic spectrum. But these are not really the ends. You can definitely have gamma rays that are more energetic than anything we have seen before. It's certainly possible that such gamma rays can be emitted. Theoretically, absolutely possible, right? See, what is the constraint? What is the highest frequency or energy gamma ray that we can find that can be detected theoretically? The higher the energy, the higher the frequency, the shorter is the wavelength of a gamma ray. Okay, what is the shortest length that's physically possible in the universe? It's the Planck length, 10 raised to minus 35 meters. 10 raised to minus 35 meters. And the highest energy gamma rays have a wavelength of about 10 raised to minus 12 meters. So there's a tremendous amount of leeway that we still have. You could have ultra high energy gamma rays and whatnot. So the hard limit is the Planck length when it comes to the wavelength. The shorter the wavelength, the higher the energy, but it can't go shorter than the Planck length as far as we know from the understanding of physics that we have. So that's the highest energy gamma ray that we can ever detect theoretically. Doesn't mean it will actually be possible in the real universe. On the other end of the spectrum, we have radio waves, which have a wavelength of about 10 raised to 3 meters, 1 kilometer. But it's possible you can have photons with a wavelength of a light year. Why not? It's possible. So what is the hard limit there? The hard limit is a photon with a wavelength that is the size of the observable universe. That's going to be an extremely low energy photon, but theoretically possible. So there we have it. There's certainly a possibility of discovering radiation that's more energetic than gamma rays and way less energetic than radio waves. Both sides of the electromagnetic spectrum can be extended. But what about other types of radiation? Non-electromagnetic radiation, non-photon radiation. See, when a star goes supernova, it emits tremendous amounts of neutrinos. So that's one type of radiation. The sun emits neutrinos. Trillions of solar neutrinos are passing through our bodies every second. That's another type of radiation. Ultra high energy cosmic rays. The most powerful, the most high energy cosmic ray ever discovered until about a decade ago was called the Oh My God particle, which was way more energetic than the most powerful, most energetic gamma rays ever discovered. So there is that as well. And once again, even gravitational radiation is a different kind of radiation. So it's possible that we could discover, other non-electromagnetic types of radiation that could be potentially more energetic than gamma rays, for sure. Yeah. Shri Chinggis Khan says, how dangerous is it for humans to cross the Van Allen radiation belt? Okay, first of all, what are the Van Allen radiation belts? These are two radiation belts. See, the Earth has a magnetic field. The magnetic field does a great job of trapping solar radiation, thereby shielding us from the harmful effects of radiation. And this solar radiation is concentrated in two belts around the Earth, which are called the Van Allen belts. Let's take a look at that. radiation belts. So these are donut-shaped belts, essentially. There are two of them, as you can see here, inner one and the outer one. And one of these, it traps electrons, the other one traps protons. Now, clearly the radiation here is higher than what we experience. The radiation in these belts is higher than what we experience on the surface of the Earth. The radiation is going to be higher. So if you spend time in those radiation belts, it's going to have an effect on you. So the Apollo astronauts went through the belts. On a single lunar mission, you would have to go through the belts twice. Once going towards the moon, the second time coming back to Earth. So we have data from the Apollo missions. So every time you cross a radiation belt, it's like getting a CT scan. That sort of radiation. Not going to kill you, not going to cause cancer, but you don't want to have it happen every single day, right? So the Apollo astronauts, there would be in a rocket which had shielding, aluminum and water and whatnot, and it was traveling at a significant speed. The velocity was in excess of the escape velocity of Earth. It went towards the moon and came back. So 2 journeys through the belt, and each time the exposure was about that of a CT scan. So not terrible. But if you spend an extended amount, if you spend, let's say, an hour in a belt, you may get about a CT scan's worth of exposure. But if you spend a week there, it's gonna cross harmful thresholds. So the key is to spend as little time as possible in these radiation belts, get out of there as soon as possible. If you are an astronaut in low Earth orbit in the International Space Station, once again, we ensure that the International Space Station is below and as far away as possible from the radiation belt so that the exposure is minimized. And yet, you're going to have more exposure than if you were on the surface of the planet. And this CT scan equivalent radiation data, it's not just about the radiation belt, the Van Allen radiation belt, but also cosmic rays. So all of that put together, it's like a CT scan, one dose of a CT scan exposure, that sort of thing. There are certain satellites that have to be placed in the Van Allen radiation belts for whatever reasons. And those satellites need hardened materials, hardened electronics, without which they die. And even with all the precautions that we take, the satellites have a lower life expectancy than a regular satellite which is not in the Van Allen radiation belt. So clearly it's dangerous. I remember there was this Russian spacecraft that was supposed to go to the moon. I think it was called Phobos Grunt or something. And that spacecraft, it did not have hardened electronics and it died in Earth orbit before it could even start the journey towards Mars. So yeah, dangerous for electronics, for satellites, and definitely for human beings. Now, what about human beings going to Mars? That takes about 8-9 months. We're going to have the astronauts pass through the Van Allen radiation belts, but then after that, they're out in open space. And they'll be exposed to solar radiation, solar wind, coronal mass ejections, and also cosmic rays that come from outside the solar system, outside the galaxy at times. Now, that is going to be dangerous. And that could cross over into a threshold where the probability of developing cancer over your lifetime is higher than normal. So such spacecraft will need additional shielding and additional precautions to ensure that the astronauts don't develop cancer or don't have a higher risk of developing cancer. So that is definitely going to be an issue, traveling to a place like Mars. But going to the moon and coming back through the Van Allen radiation belts, it's not going to be a very big issue unless you get stuck over there for whatever reason, or unless you are passing through the radiation belt, and at the same time you're hit with a solar flare or something, or a solar storm. Then your exposure will be higher. So it's complicated. There are all these different parameters that you have to take into account. Udit Mahesh says, why do many countries have space stations in the easternmost coastal regions of their territory, like Sriharikota for India and Florida for the United States? Great question. See, we know that the planet Earth rotates around its own axis. How do we know it? We have day and night. Can you guess what's the direction in which the Earth rotates? Let me give you a hint. Where does the sun rise? Which direction? East or west? It rises in the east, which means that the Earth is moving in the direction of the east. It's moving from west to east, not east to west. Okay? So we know that the Earth is moving from west to east. The rotation is in that direction, which is where the sun rises in the east. Now that we understand that, what is the speed of the rotation? If you are standing at the equator, the rotational speed is about what? 1600 kilometers per second, which is massive. Massive. So if you have a space station in Sriharikota, which is close to the equator, then you're going to have a massive, then when your rocket takes off, it's already going to have this 1600 kilometers per hour boost before it even begins to take off. So that way you have to spend less fuel to get this rocket into orbit. Similarly, if you're at Cape Canaveral, Cape Kennedy it's called now, on the south coast of Florida, and if you take off from there, it's going to get this massive boost from Earth's rotational speed. And the added advantage is that if something goes wrong with the rocket, you can simply splash the rocket down into the Gulf of Mexico or in the Bay of Bengal, and it's not going to hit any land. So that's why India and the US have space launching centers on their east coasts near the equator with the sea to the east. Makes a lot of sense. Okay. Critical Thinker says, why does fire have a shadow? And what is the physics behind shadows? First of all, physics behind shadows. For a shadow to occur, you need a source of light. You need a surface where the light will be incident. And you need something between the source of light and the surface that either blocks the light, absorbs the light, or what is it? Reflection, absorption, refraction, or refracts the light, which means it absorbs the light and emits it in a different direction. That way, there's going to be a blockage between the source of the light and the surface, which will be observed in the form of what we call a shadow. Okay, that's the basic physics behind shadows. Now, why does fire have a shadow? So what is fire? Fire occurs when something burns. Let's say you have a candle. What is the fuel? It's the wax. What is the thing that is set on fire? It's the wick. Now, what is fire? This flame that we see, what is it? What does it contain? It contains carbon dioxide, it contains water vapor, it contains oxygen, it contains various gases, it contains carbon particles, soot particles, it contains various organic compounds that come from the breakdown of the wax, and it contains very high temperature gases that emit photons, light, that we see in the form of a flame. And these gases, they go upwards because they're so hot, which is why a flame stays upright. Okay, so that's a flame. Now, let's say I have a flame here. I have a surface here. I've got a source of light here. And let's say my source of light is brighter than this flame. So the light will go this way. It will hit the flame. And the flame has different gases at different temperatures. And these gases, etc., so some of the soot particles will block some of the photons and absorb those photons. Some of the parts of the flame will refract the light and make it go in different directions instead of going straight through the flame. And because of the combination of these factors, not all the light that's emitted from my source will be incident on the surface. Some of it will will either be absorbed by the soot particles or will be refracted in other directions. And because my source of light is brighter than the flame, you're going to see a shadow on the surface where the light is incident. So you're going to see this area where the light is fully incident with full brightness, and there's going to be this shadow of the flame. That's how a flame can have a shadow, only if the source of light is brighter than your flame. If the source of light is dimmer than the flame, you will not see a shadow. Okay. Feminist Slayer says, what is another dimension? In films or anime, when they say that they have moved to another dimension, does it mean that they have gone to a different universe or a different world? What is the deal? What's a dimension? What are dimensions? See, we perceive dimensions: length, breadth, height. I have this object here. It has a certain length, a certain breadth, and a certain height, very small height, right? So these are the three dimensions, physical dimensions that we are aware of. What it means, what is a single dimension? It's a place where you can go either forward or backward. That's all. A place where you can go forward or backward. So if I have a sheet of paper and I draw a line on it, I can only go forward or backward on the line. But if I have the whole sheet of paper, then I can go forward or backward in this direction, forward and backward in that direction, and whatever the direction. So that's two dimensions that I have. But if I have a box, in that case, I can go forward and backward in all kinds of directions, all three dimensions. So that's three dimensions. And then we have a fourth dimension called time, which in the equations can go backward and forward, but we only perceive one direction. So those are the four dimensions we can understand. Now, in films, anime, etc., they will say that there are other dimensions. What is that? So in string theory, you have either 10 dimensions or 11 dimensions. So these are other directions that you can go backward and forward in, but those dimensions are compactified. They're so small you can't perceive them. Let's say you have an ant that's walking on a very thin wire. If I am seeing it from 5 meters away, I can barely see the wire and barely see the ant. And it looks like the ant is walking on a single dimension. But if I take a magnifying lens or a microscope and I see, and I observe what's happening, I will see the ant is walking on this cylindrical surface. And from the ant's perspective, it is a three-dimensional object. So that's an extra dimension that the ant perceives, but from where I am, I can't perceive it because it's so small. So similarly, in string theory, there can be 10 or 11 dimensions, apart from beyond the four that we perceive. And these are all compactified, very tiny microscopic dimensions, which is why we can't perceive them, right? So that's dimensions. Now there is something called brain world theory, brain cosmology. In brain cosmology, what it essentially says is that our universe is a four-dimensional surface on a higher dimensional bulk. So the higher dimensional bulk may have more dimensions than the four dimensions we perceive and observe. And the universe is simply a four-dimensional projection of that of that higher dimensional bulk. And there could be other membranes or brains like our universe on the same bulk, which would be other universes. So that's another. So in brain world theory, brain cosmology, you could have other universes that inhabit the same bulk that we inhabit, but are separate parallel universes. So that's different dimensions, you could say, from that, pop culture perspective. But in films, anime, etc., when they say another dimension, they mean another universe. That's just a layperson's way of simplifying things to make it interesting. It doesn't. In a film, anything's possible, right? It's a blend of science fiction and fantasy. So you can make up any story, you can make up any rules. As long as the rules are consistent, the story is interesting. Okay, let's take one or two more questions because we have gone way past 2 hours. Critical Thinker says, can a star turn into a planet? Why is Jupiter called a failed star? So let us define what is a star and what's a planet. Okay, a star is a gigantic fusion reaction. It's a gigantic collection of hydrogen and helium, that is typically hydrogen and helium, that is so massive and self-gravitating that the combined pressure of the atoms is so high that at the very core, of this collection of atoms, the temperatures and pressures are so high that they ignite the fusion of hydrogen into helium. And this fusion reaction, it pushes back against the gravitational crush of the collection of atoms. And that's why the star becomes spherical and it burns for billions of years. So that's a star, typically hydrogen and helium with trace amounts of other elements. That is a star. What is a planet? A planet is a byproduct of the formation of a star. So how does a star form? You have a huge collection of gas, mainly hydrogen, helium, that starts self-gravitating, that starts coalescing towards the center, and because of the motion, it becomes a disk, and the disk has a rotation, and at the center the star ignites, and whatever is left around the star out of the original disk, all of that clumps into planets. So planets are byproducts of the formation of a star. Planets can be rocky or gaseous. Rocky planets are Earth, Mars, Venus, and Mercury. Gaseous planets are Jupiter, Saturn, Uranus, Neptune. These are examples. So stars are very different from planets. Stars cannot become planets. Now, why is Jupiter called a failed star? I don't know who calls Jupiter a failed star. I think it's just popular. It's a popular way of talking about Jupiter, but Jupiter is a very successful planet, actually. It's a very successful planet. Why is it a failed star? Let me explain why some people call it a failed star. It's because Jupiter has the same composition as the sun, hydrogen and helium, mostly. So it's the same composition as the sun. The sun is an active star. It's shining. It's fusing hydrogen into helium. But Jupiter hasn't been able to do that. So that's why some people call it a failed star. Now, here's the deal. Jupiter is a very successful planet, but it's not a failed star. What does it take for something like Jupiter to become a star and ignite fusion? You need a mass of about 75 to 80 Jupiters taken together for the gravity to be enough to ignite fusion within. So the smallest proper stars have a mass of about 75 to 80 Jupiters. So if I take a Jupiter and I take 75 or 80 other Jupiters and I bring them all together, then the combined planet will turn into a star because nuclear fusion will ignite. There's another limit, 13 Jupiters. If you bring 13 Jupiters together, then deuterium fusion begins for a while and then stops. So that sort of object is called a brown dwarf. A brown dwarf is a failed star. There is some fusion for a while and then it stops. Okay, so Jupiter mass to 13 Jupiter masses, you just have a planet. 13 Jupiter masses to about 75, 80 Jupiter masses, you have a brown dwarf, which is a failed star. And 80 Jupiter masses onwards, you have proper stars. That is the deal. So Jupiter isn't really a failed star. It's a very successful planet and a very beautiful one at that. Okay. Let's take one more question. This is by Mary Kane. Mary Kane. In 1945, nearly 16,000 girls or women from India, the UK, and the US, WRINS, etc., worked together code breaking using skills like pattern recognition, memory, and mathematics to help bring an end to the Second World War, later remaining under secrecy laws for decades. The youngest girl would be about 95 to 100 years today. So two questions. First of all, in the case of an alien invasion from outer space, do you think the same math skills are just as relevant today? And number two, what would you do as an educator to make sure that every girl has the opportunity to excel in science as per her aptitude and interests? Okay, firstly, in the case of an alien invasion from outer space, would these skills, math skills, code breaking, pattern recognition, memory, mathematics, etc., will those same skills be relevant today, just as relevant today, to counter an alien invasion from outer space? You see, this code breaking, etc., which was done during the Second World War using skills like pattern recognition, memory, mathematics, etc., this was done to counter a human threat. It was the Allies against the Axis. So you had things like, breaking the Enigma code, etc., the Enigma machine, which was a brilliant cryptographic invention by the Germans, and Alan Turing and his team, they were able to crack the code. And you had this program as well, 16,000 girls. So all of this code breaking, etc., was done to counter human threats, to counter human intelligence. It was human intelligence versus human intelligence, right? Now, if you have an alien invasion from outer space, that presupposes that this alien invader species is going to be capable of traversing tremendous interstellar distances and reaching our planet, which means that their technological capabilities will be way higher than ours, which means their intelligence is going to be way higher than ours. Let's say a sufficiently intelligent human being has an IQ of, let's say, 150. Then it means that these aliens may have an IQ of 400, 500. And no amount of pattern recognition, memory, or mathematics or whatever is going to be able to defeat those alien invaders. So if there's an alien invasion from outer space, none of your technology, none of your mental attributes, intellectual attributes, technology, whatever, none of it will be able to defeat the alien invaders. If there's an alien invasion, if aliens turn up at our doorstep, having come from God knows how many light years away, we're done, we're cooked. There's nothing that can save us, unless the aliens make some stupid mistakes like what they show in science fiction movies. So that's number one. Number two, what would I do as an educator to make sure that every girl has the opportunity to excel in science as per aptitude and interest? First thing, I would have a level playing field. Everybody gets the same starting point. Everybody is treated equally, and everybody has to play by the same rules. There is no selective rules for different rules for different people, essentially. So an education system has to be gender agnostic. It doesn't matter what the gender of the student is. Everybody has to be treated the same. Everybody has to be given the same opportunities and the same rules to play by. That's number one. Number two, the entire system has to be based on merit. And number three, the system should be such that it seeks out and rewards talent and aptitude and the capacity to work hard, etc. You do these things, everybody will excel, not just girls, but everybody who's good enough will excel as per their aptitude and interest. That's what I would do. I would not do it specifically for girls. I would do it for everybody. I would treat everybody the same, because human beings have to be treated the same, irrespective of their gender or color of skin or whatever else. That's what I would do, and hopefully everybody thrives under that. Okay, that brings me to the end of today's questions, to today's live stream. I still have more questions that I have selected, but I won't be able to take them today, maybe in the next session. Let's see what kind of live chat we have. We have a whole bunch of... So we have Praveen Reddy is a new member. Thank you so much, Praveen Ji. Welcome to membership. Thank you very much for becoming a member. VSVS, namaste. Thank you very much. UMX is talking about geopolitics. We will discuss geopolitics and see. Let me see the different super chats. Do any of them have anything to do with science? Voynich manuscript is not science, it's history. James is talking about English. UMX is talking about Sudan. Balki today is Rishis. Listen, I do not mix religion and spirituality with science. When we talk about the concepts developed by our rishis, we're talking about a certain period in the historical development of science that was several thousand years ago, when we did not have the understanding of science that we have today. So we can't mix that with what we have today. Initially, there was no clear understanding that you have to keep science and spirituality separate, science and religion separate. So you had people who did everything at the same time. They talked about God and science in the same breath. Science is all about the material observable world and observable phenomena and replicable phenomena. There is no concept of spirit or morality or God or demons or whatever in that. So you can't mix these two things. I am very clear about this. So that's all I can say about this matter. There are all kinds of ancient concepts that have elements of science in them. And if India's civilization had not been destroyed 1,000 years ago, then we would have made tremendous advances by now. But all we are doing today is talking about what happened thousands of years ago, which is not really part of this discussion today on science. Once again, this is about spiritual experiences, which is not science. NPS says Fermi paradox only indicates there are no type 2 or type 3 civilizations in Milky Way, as their heat signature would be recognizable, but there can be type 0.8 civilizations at par with us. What's my POV? The Fermi paradox asks a simple question. Where is everybody? The Drake equation talks about how many civilizations, intelligent civilizations, there could be in a specific galaxy based on a number of criteria and parameters which we don't know how to quantify. Okay? As far as I understand, the Fermi paradox doesn't say that, type so-and-so civilization. So you are bringing in the Fermi paradox, you're bringing in the Kardashev scale, you're also bringing in somehow the Drake equation. The way I see it, the Fermi paradox asks a simple question. Where is everybody? You have 10 raised to 22 or 23 possible planets, stars in the observable universe. Let's say each star has at least one planet. So you have 10 raised to 22 or 23 or 24, 20, let's say 10 raised to 23 planets in the observable universe. Let's say 1 in a million of these is Earth-like. So that's 10 raised to 17 or 16. Let's say one out of a million of these has developed life. So that's 10 raised to 10. Let's say 1 out of a million of these has Earth-like, human-like intelligent life. That's 10 raised to 4. So there should be at least 10,000 human level or higher civilizations in the observable universe. If you're very skeptical, it's still 10,000. So where is everybody? Why can't we see anything? That's what the Fermi paradox asks. It doesn't talk about the Kardashev scale. Right? That's how I see it. Biju says, what's the actual color of our sun? It's white. But what do we see? We see yellow, right? It's still white. Why is it? It's because the Earth's atmosphere, it sucks out certain colors. Okay, let me show you something. There is something called the color wheel, the HSL wheel. Okay. Oh, what's that? 1 second. Give me a second. Let me put this on the screen. Okay. The color wheel. Let's talk about two colors, blue and yellow. They will be on the opposite ends of the color wheel. Okay. Let's see. Color wheel. See where is blue, where is yellow. Yellow. Opposite ends of the color wheel. So the sky becomes blue, doesn't it? And the sun appears yellow. If you add blue and yellow together, you get white. Kind of like that. So it's because of the atmosphere absorbing certain wavelengths from the white light of the sun, which is why the sky becomes blue and the sun appears yellow. But if you go outside of the atmosphere and look at the sun, maybe dim it a little bit, it'll be white. So the sun is a white star. Biju says, why is the time considered to be fourth dimension? Because you can call it the first dimension if you like. But it's because we consider the spatial dimensions to be the 3 dimensions we see. That's why time is called the fourth dimension. You can give it whatever title, whatever tag you want. You can call it the 0th dimension if you like in your physics. It won't affect the equations. So it's about why have we given a certain title to this? Why do we call this lime color? Why don't we call this something else? Doesn't matter. It works the same. Okay, that brings me to the end of today's session. I apologize to the ones who have taken super chats about topics that are not connected to science. I will only take science questions today. I have repeatedly requested everybody, if this is a question about a certain topic, let's talk about that topic only. Otherwise, I'll break my rules, and then if you have no rules, then you have no discipline in life, and everything goes to hell. So I will only discuss science today. But that brings me to the end of today's live stream. I hope it was something that gave you some value, maybe some better understanding of the universe, the world. And I look forward to seeing you in tomorrow's live stream, which is going to be about anything. So ask me anything tomorrow in the super chat, and I'll take as many questions as possible tomorrow. Until then, take care, keep learning, keep asking questions, and I will see you tomorrow. Thank you, everyone. Bye-bye.